I'm Dr. T, and welcome to my whiteboard. Today I'd like to talk about heat. And to do that, let's get a little bit of things out of the way. So we are talking about energy, but energy actually comes in two flavors. So, of course, energy, broadly defined, is the ability to do work, so we could say that energy equals work. But, of course, we'd have to say what work is. And that is acting on a substance in an orderly fashion. Now, of course, you don't always have to be orderly, and you can be nice and disorderly, and that's what we usually mean both by heat. So we could say that energy is the amount of action you're taking on a substance, both in an orderly fashion, work, and in a disorderly fashion, heat. And as chemists, we're going to try and avoid the work as much as possible. We like that chaos. Okay, so to talk about heat, we got a couple of things we need to start talking about. For starters, heat is not temperature. Oh, by the way, heat gets the symbol Q. The historians are still trying to figure out why, but basically one of the early researchers in the late 19th, early 20th century said, let's use Q, and everyone used Q because, it works. Okay, heat is an amount of energy. It is a total sum of energy, and it's always going to be an amount of energy going from one thing to another thing. You can't really measure the total amount of energy in a thing. It's just too complicated of a mess. So you're always dealing with the energy moving from to another. Temperature, on the other hand, is looking at more of an average kinetic energy of your particles bouncing around. That's an imperfect definition. It's definitely a little bit more going on there, but it is definitely a functional definition that as chemists, it's generally good enough for what we're doing to understand what's going on with temperature. That said, temperature is dealing with kind of an average quantity of a substance that's measurable. Heat is, one, difficult to directly measure. Usually you measure it indirectly via temperature. And, well, it's moving between. And it's an absolute amount, not an average. Other quick point. Lowercase t, that's time, not temperature. Capital T, that's temperature. So do mind your capitalization. It does make a difference because temperature and time are completely different things. Okay, so I mentioned how we measure heat indirectly via temperature. Let's talk about that. So to do this, we're going to need a tool or an instrument, and that instrument is a calorimeter. Now, I'm setting up currently a fairly simple calorimeter, a case where you're not actually doing any chemistry, you just simply have something that's hot or cold that's sitting in something else, therefore heat is moving around. A calorimeter is an insulated container, first and foremost. Now, it has two parts. The system, that's the thing you are studying. And whenever we're talking about dealing with heat and what we call calorimetry, or the use of calorimeters, we're always talking about the system. Although that gets a little bit confusing because everything else is what we call the surroundings, and everything else is going to be acting in reverse to the system. So if heat is flowing out of the system, it must be going somewhere, and that is the surroundings. It's going to feel hot because you're the surroundings. And if it's going out of the system, it's going into something, and potentially you. Now, the calorimeter, the goal of the calorimeter is to limit the surroundings, at least in practice, to a manageable area. Without it, you'd have to track heat change in like Antarctica, and it gets a bit complicated. This way, it's just in a small container, or for the most part. Okay, so if heat is flowing out of it, we call that exothermic, and as I mentioned earlier, it will feel hot. If heat is flowing into the system, that is what we call endothermic, and it will feel cold. Because that heat is flowing into the system, it must be coming from the surroundings. And once again, if you are holding it, you are part of the surroundings, so it is taking your heat. Now, we can measure the amount of heat shuffling around if we know a couple of features. First, we're going to need to know a couple of things. One, the mass of our system. Yeah, is exactly what you think it is. The next is what we call specific heat, and this is a property of different substances that describe how much they respond in terms of temperature to an added amount of heat. Certain items will increase their temperature very readily with only a small amount of heat added, while others will increase their temperature only a little bit, even with a fairly large amount of heat added. This feature is known as specific heat. By the way, if you're familiar with heat capacity, that is the multiplication of mass and specific heat. Obviously, the more stuff you have, the more energy it's going to take to increase its temperature by the same amount. The last term is actually two terms, and that is one, delta, and that's simply saying we're going to look at the change in whatever's attached to it, and of course capital T is temperature. So in this case, I'm going to be looking at the final temperature that my thing is going to be at, so after I have added the heat, and subtract off the initial temperature, however much it started with. Yay. Now, if the initial is smaller than T final, this will be a positive number, Q will be positive, and this was endothermic. It has gained in temperature, it has gained heat. If this number is smaller, then this will be negative, and Q will be negative, and it was an exothermic event where it had lost heat. Obviously, if it loses heat, something else gains it. Now, a little bit more math. This equation would apply to the system or the surroundings. Since it's hard to measure heat directly, although we definitely could simply use this one to measure it indirectly, quite often we're not actually looking for Q. We're looking for something else, like change in temperature or the specific heat of a substance, because specific heat does let us know some information about what we have, such as potentially what is it, or more likely what it's not, as each item does tend to have a fairly standard specific heat for what it is. So we'll combine the equations. Yay. So I've got my calorimetry equation for my system. Note the subscript SYS for system on here. And this is literally just that. No different, just write down. Now, I have one other quick point. The Q of the system is the same as the Q of the surroundings, but times -1, because it's going in the opposite direction. There's this frame of reference shift. So I'm going to take this equation, and I'm going to drop it down. Of course, I'm going to put surroundings, SUR notes on all of these. And then I'm going to put on the -1. You will see this quite often in many textbooks, with the -1 being on the delta T and the TF and the TI flipped. I found that's just a really good way to mess up the math. So I just put it off to the side. Makes your life much easier. And so, with our equation, if I know any, say, most of them, all but one, then I can solve for whichever one I don't know. I should point out, by the way, because in a calorimetry scenario, the system is in the surroundings, we can make a fairly straightforward assumption. The T final of the system and the T final of the surroundings are going to be the same. So now I have 1, 2, 3, 4, 5, 6, 7, not 8 terms. As long as I know 6 of them, I can find the 7th, whatever it happens to be. Yeah. So next up, let's work some math. Okay, so let's work through some math. And in this scenario, I have surroundings in a system, standard calorimetry. This would be presumably some kind of unknown metal object, and a calorimeter. And I'm going to assume that the calorimeter is filled with water. This is a very popular approach, definitely not the only one. Obviously, if you've got things that water shouldn't be around, then obviously you don't want to do this. And there are definitely vacuum-filled, air-filled, various other types of calorimetries. But a calorimeter that is an insulating container filled with water is a very popular approach for cases where that will work. It's an inexpensive and effective approach. Okay, so in this case, I've got the calorimeter, which is the surroundings. I've got the unknown metal object, which is the system. And I've got some information about it. T final, which is going to be the same, is 32.1 degrees Celsius. T initial for the metal object is 97.3 degrees Celsius. The surroundings, it's 19.2 degrees Celsius, a little bit chilly apparently. The mass for our system is going to be 52.1 grams. The surroundings, so the water in the calorimeter, is 73.6 grams. Specific heat for water is 4.184 joules per gram degree Celsius. By the way, I should point out that these degrees Celsius, because they're going to be into a delta, and you're going to do a subtraction, if they were Kelvin, that would be fine too. And you could use these in Kelvin, that would still be a degree C, it would be fine, because if you recall, the degrees, the actual size of the increments with Kelvin and with centigrade are the same. And since you're subtracting, you're caring only about the size of the units, not the absolute scale. And then I don't know what my specific heat is because apparently I don't know what my metal is. So I could use this to try to figure out what the metal might be, or at least rule out possible choices. Okay, so I'm going to look at some math. I'm going to start out with that calorimetry equation we looked at earlier. So this is the same as you saw previously, just moved up to the top. Phase 1, I'm just going to start plugging in all of my numbers into this equation. And from this point out, it is literally just algebra. So I'm going to condense my deltas, get me some numbers over here. Now, by the way, at this point, quite often, I will actually go ahead and just get rid of these minus signs. The thing that will give you the most problems are those minus signs. They are the bane of your existence in this particular algebra because it's easy to mess it up. Okay, next up, I'm just going to start condensing, moving it over. Once again, good old-fashioned algebra. Finally got myself an answer for the specific heat. Of course, I use a question mark. I like to use question marks for my unknowns. That way it's pretty obvious what it is. And then round to proper sig figs. For reference, metals tend to be, this would actually be a little bit high for most metals, so the aluminum is over 2. Most metals are going to be kind of in the 1-ish range. Water, of course, is 4.184. This is actually really high. Most things are not going to have specific heats that are this high. And all specific heats are positive. If your specific heat is negative, obviously that minus sign has got you. So you're going to have to go back and figure out what's going on with that one. Now, I should also point out that the specific heat of water being this high actually has a lot of effects. So if you imagine desert regions with very low amounts of water, because it doesn't have much water, the soil has specific heats closer to that 1-ish range. The solar heating is able to do a much more extreme temperature swing. During the day, it's able to heat it up, considerably hotter, so specific heat is much lower. And at night, it's able to give up a lot of the heat, and it's going to get a lot colder in those regions. Wet regions, hey, you got a lot of this water, it's going to take a lot of heat to heat it up, and once it's hot, it's going to take forever to heat it or let it cool down. Okay, so this is solving for specific heat, and of course we can also solve for our temperatures if we would like to do so as well. Okay, so now I have a similar calorimetry problem as the previous one. The major exception, though, is I know my specific heat for both of my substances. However, I don't know what my T final is going to be. And algebraically, this is the one that's the most a pain to sort out. So I've got my information. I'm going to use the exact same equation. I'm going to plug everything in. Phase 1, I'm just going to simplify it. Anytime I can just clean up some math, I'm going to go ahead and do that. Beware the minus sign. Those will throw you. Okay, so I'm going to start cleaning out some math. I'm going to go ahead and do a little bit of distributing. Once again, be careful with that as well. That's another trap that you can fall into. And then I'm just going to start moving things from one side to the other with the intention of getting rid of negative signs. So like, okay, if I move the joules to, say, that side, take this part, and then I'll get rid of the minus sign. So right now I just have a rather ugly set of algebra, and I'm just going to keep going with my ugly algebra until eventually I get myself a number, 30.9. As soon as I get myself a number, I'm going to have to do a couple quick checks. One, this is in degree C, so it could be negative, but it's going to have to be between the two T initials. It's not going to heat up hotter than the hotter of the two, and it's not going to cool down cooler than the cooler of the two. So this is 30.9. What were my T initials? My T initial for the system was 98.5. Okay? And my surroundings is 18.3. 30.9 is in between those two, so this is looking good. Usually if you mess up the minus signs, what you're going to see in this setup is that you're going to get a T final that is outside the window of your TIs. It'll either be much higher or noticeably higher than your hot one or cooler than your cold one. And immediately you know that's not going to be quite right. You should be looking at, somewhere in the middle, depending on your masses, how close to each one. Typically, if you've got water, because it's high specific heat, if the masses are even reasonably close, it's going to be a little bit more towards the water side of the equation. But otherwise, yeah, I want you to take a little bit more look at this hideous algebra. But that's about it. Have a wonderful day.